Okay. Good morning, everyone.
Good morning.
Good morning, sir.
Good morning, sir.
Good morning. Good morning. Good morning. Okay, great. So, are you able to see my PPT in full screen mode?
Yes, sir.
Okay, great. So, in last session, we discussed about different properties of the material. Okay, and we observed the behavior of electric field in metals as well as in dielectrics. Okay, so there was a question how current flows through the dielectric. So we do have now understanding of a concept that is polarization, where your electric dipoles are created due to influence of the externally applied electric field. तो ये चीजें देखी थी. यहाँ पे एक important word है electrostatic. What do you mean by electrostatic? Or what do you mean by magnetostatic? Okay, we need to analyze these words. Okay, electric field. Magneto is magnetic field. And static means it do not change with time. Remember that it do not change with time. Okay, throughout our discussion we never observed a quantity like dabba by dabba t. Okay, nothing is varying with respect to time. Yes, we have seen dabba by dabba x or dabba by dabba y or dabba by dabba z and rest of the partial differentiations in other two coordinate system, because your field may vary with respect to space coordinates. Okay, space coordinates हिसाब से वो change होगा, लेकिन at a point in the space, अगर वो फिलहाल अगर electric field is something like 4x ax cap plus 3az cap, अगर यहाँ पे at t is equal to 1 है, इतना amount है, this is a electric field intensity at a certain point in the space, तो t is equal to maybe 4 lakh years. उसके बाद भी वो वैसे ही रहना, it is not going to change with respect to time. सिर्फ एनालॉजी देने के लिए बोला है टाइम इज इक्वल टू 4 लाख years, otherwise we never talk about this amount of time. Okay, and whenever we say that the fields are changing with respect to time, then those are no more static, but those becomes dynamic. Okay, and we are also going to see the behavior of dynamic fields in the dielectric materials, but right now we are looking at the static fields, static electric field, and we have observed the concept of polarization. Okay, what happens in polarization? If no externally applied electric field, then we do have symmetry in the atom. Under the influence of externally applied electric field, at electron तो ज़्यादा electrons आ जाते हैं compared to this side, so we can say that this part of the atom is more negative compared to this part, so we call it as, okay, we have created a dipole. Okay, and there is some distance d in between it, in between the two poles. With this understanding, now in today's session we will analyze the capacitors. Okay, capacitors do have your, let us say, a parallel plate capacitor. Okay, we do have two parallel plates, and in between we do have our dielectric medium. Okay, so what happens to one plate? We apply certain charge to it, and what happens to another plate? Exact amount but opposite in polarity charge develops. Okay, and the question is, dielectric is an insulator. Dielectric is an insulator, but still we do have this observation: equal and opposite charges are developing on the another plate. Okay, Now we do have an answer for how electric field propagates. ओके कि भाई यहाँ से इलेक्ट्रिक फील्ड आया, यहाँ पे फिर चार्जेस डेवलप हुए, सॉरी डाइपोल्स डेवलप हुए, एंड समथिंग समथिंग हैपेंस. But still, till date we don't have any answer how charges are developed. Okay, on develop on opposite plate. इलेक्ट्रिक फील्ड आ रहा है, फाइन, नो वरीज, लेकिन ये निगेटिव चार्जेस कहाँ से आ रहा है? टिल डेट वी रियली डोंट हैव एनी concrete answer for that. Yes, we do have lots of theories about it. Okay, so keeping this question in mind, ki how charges are developed or how current flows. Okay, how current flows, we have a theory called as displacement current, which we are going to visit in unit number 4. Okay, and this displacement current, do remember that this is still a theory proposed by the Tesla, and not really proposed by but used by what do you say, Maxwell. Maxwell and Tesla. Okay, Tesla was a very new scientist compared to all the magnetic and electric innovations. ठीक है. So moving to our part of curriculum, we will see how capacitors works, how we get the expression of capacitance, how we get the expression of capacitance. Okay, before that, one experiment. Let us read this statement in the left hand side top corner. Okay, I wish to inform you of a new but terrible experiment which I advise you on no account personally to attend. भाई कुछ भी कर लो, मत परफॉर्म करो. ओके, क्यों? क्योंकि ये जो बंदा है और ये जो बंदा है, क्लेस्टन पीटर कहते हैं, चलो पीटर वैन कहते हैं, तो they were doing some sort of capacitance experiment, trying different materials, and he said that the snapping sparks that jumped from the iron tube to the finger there upon my right hand F was struck with such force that my whole body quivered just like someone hit by lightning. इतना जोर से शॉक लगा. The arm and entire body are affected so terribly I can't describe it. I thought I was done for. बस भाई मैं तो मर गया. The globe D, ये जो globe D बनाया था उन्होंने, okay, that almost killed me was a very thin white glass, 5 inches in diameter. Thin white glass का था उन्होंने globe बनाया हुआ. Okay, and I found that I found much about electricity that I have reached the point where I understand nothing and it explains nothing. तो भाई ये था starting of the capacitance. इतना डर गए थे लोग उस टाइम में कि भाई we really cannot handle the charges and we really really cannot control it. But nowadays we know that lots of every electronic equipment do have capacitors in it. Okay, so this was the starting of capacitance. Everyone was frightened, and especially this person. Oh, don't attempt that, it will kill you. Okay, so moving on to the very interesting component, capacitance. So we are going to study three types of capacitors: parallel plate capacitor, spherical plate capacitor, and sorry, spherical capacitor and coaxial cable capacitor. So we do have some construction and assumptions over here. So we do have our coordinate system and two plates containing plus rho s and minus rho s charges, charge density, surface charge density on them. So since upper plate contains plus rho s, we assume that the direction of electric flux density is from top plate to bottom plate. These were our assumptions or experimental setup. It consists of two plates of area A and separated by distance D. इसका भी area A है, इसका भी area है, and the distance between the two plates is D. Okay. Let plus rho s is surface charge density uniformly distributed on the upper plate. Plus rho s कहाँ पे है? Upper plate. Then according to Gauss law, minus rho s will be developed on the lower plate. Fine. This means flux density d bar is moving from upper plate to lower plate along the z axis. देखते हैं अभी एक फंडामेंटल इक्वेशन पता है C is equal to Q upon V. Okay. The equation of flux density क्या कहता है? Actually we want to express Q and V in some different notations so that we will put the formula for C in different notations, means we will have something in terms of relative permittivity. Let us see. So d bar is nothing but amount of charge upon area, density है, am I right? So d bar is equal to Q upon A and minus AZ. Minus AZ क्यों लिया? Because d bar is in downward direction, minus Z axis. Okay. We also know that d bar is equal to epsilon E bar. So therefore E bar is equal to ये इप्सिलॉन को इस साइड में लेके चले गए एंड वी आल्सो पुट द वैल्यूज ऑफ Q एंड A. So E bar is equal to Q upon epsilon A minus AZ cap. Now we know that one expression talks about the potential V is equal to minus E bar dot dl bar. Here dl bar is equal to dz minus AZ cap, negative direction of Z. Okay. D bar is moving in a downward direction. So put the values everything in the equation. Okay. E bar क्या है? Q upon epsilon A. Q upon epsilon A. ओके ये dl क्या है? dz माइनस az. तो ये माइनस az और माइनस az, ये माइनस माइनस प्लस हो गया. az is equal to 1. So we are left with dz and the distance in between the two plates is d. So integration limits are 0 to d. Solving the integration we end up into v is equal to qd upon epsilon a. So put the value c is equal to qv. Q तो वैसे ही रख दिया, v का इक्वेशन क्या रखा? qd upon epsilon a. So q gets cancel out and we have expression of capacitance of a parallel plate capacitor as epsilon a upon d. This is a well-known formula. You applied this formula in 9th standard, 10th standard, maybe in the first year of diploma and the first year of engineering. But this is how it arrived. Okay. ये ऐसे हुआ इसलिए वो C is equal to epsilon A upon D. Now, what kind of numerical will be asked? आपको epsilon दिया होगा, आपको A दिया होगा, you need to find D. Okay, sorry, you will be given with D and you need to find C. ऐसे भी हो सकता है कि भाई you will have an expression of E bar, you will have an expression of DL bar, you will have an expression of D bar, and accordingly you have to solve it. Okay. So you will have this derivation, okay, part of the exam and the understanding how we end up into this formula C is equal to epsilon A upon D, a straightforward derivation. Okay, moving on to next geometry, spherical capacitor. Some things are observed over here. You do have two sphere, concentric sphere. Internal sphere has a radius A and outer sphere has a radius B. Okay, this is a three-dimensional kind of geometry and this is a cross section or 2D dimensional. So internal sphere has a radius A and outer sphere has a radius B, and in between we have a material with relative permittivity epsilon r. Let us see. It consists of two spheres of radius A and B. If gap between the sphere is filled with dielectric, then it acts as a spherical capacitor. If we keep air, okay, air is also a dielectric material, it will act as a capacitor. So V is equal to minus integration RB to RA E bar dot DL bar. Okay. So we have an expression of V. Here E is expressed as Q upon 4 pi epsilon R square AR cap. तो E का है expression अपने पास. DL bar क्या रहेगा? Since we do have something in the radial direction, okay. So DL will be DR AR cap. Put the values into the integral. So we will have take out everything constant. So Q upon epsilon 4 pi epsilon will be outside, okay. And this negative is as it is over here. And AR cap dot AR cap will be 1. So we are left with 1 upon R square. Okay, 1 upon R square. And the outer radius to the internal radius. So B to A are the integral limits. So solving the integral, so we end up into V is equal to Q upon 4 pi epsilon 1 upon A minus 1 upon B. Let us say this is an equation number 1. Since capacitance is Q upon V, so we can write down C is equal to Q upon, ये जो V का एक्सप्रेशन निकला था ना यहाँ पे रख दिया, Q upon 4 pi epsilon 1 upon A minus 1 upon B. Okay, so let us cancel out the Q and we will have expression of capacitance C is equal to 4 pi epsilon 1 upon A minus 1 upon B. What is A? A is radius of inner sphere and what is B? Radius of outer sphere. So if I give you radius, so we can calculate the capacitance as long as we are given with another value of permittivity epsilon r. Okay, another straightforward derivation for spherical capacitor. We do have next part. So case one.
सर
Yes, yes, yes.
सर आपण सर बॅक करा ना एक सेकंड प्लीज. सर आता आपण सर्कल विथ रेडियस ए अँड सर्कल विथ रेडियस बी च्या मधल्या डिस्टन्सचा आपण कपॅसिटन्स काढलाय ना.
बरोबर बरोबर.
सर मग ह्या इक्वेशन मध्ये सर्कम्फरन्स इक्वेशन मध्ये नाही आहेत का?
सर्कम्फरन्स कसा आहे?
सर्कम्फरन्स किंवा एरिया मोस्ट
Okay,
प्रॉब्ली.
okay. We do consider this part only. Am I right? The region in between the two spheres.
येस.
The analogy you studied probably in 11th standard or a diploma or while the preparation of JEE and AIEEE. So you studied that time in a different way, in a geometrical way. Okay. Here we are dealing with the vectors. So E bar and DL bar. Whenever we say that E bar, it is taking care of the surfaces. क्योंकि इस surface की वजह से some sort of electric field will be generated. इस surface वजह से some sort of electric field will be generated. Okay. So these expressions are actually taking care of those values, surface area or the region in between the them, in between the two spheres. अगर v की बात करते हो तो यहाँ पे देखिए इंटीग्रल लिमिट्स आर देयर a and b, and whenever we talk about area of a circle, so we do have a kind of pi r square expression. So we do have r square term over here. We do have radiuses of radii of the geometry. Okay, so somehow the area of the geometry has been taken care of. Okay, so
ओके.
we really don't see direct expression for 2 pi r, that is circumference, or we don't have pi r squared. We don't really find those direct expressions, but yes, those has been taken care of through various terms, E bar, DL bar, V. Okay. So looking at this expression now, we do have two cases. Let us see. Case number 1. What if B is at infinity? Means what? You have only one surface with radius A. और वो जो B है, outer surface जो है, it is at infinity. We really don't have it. So what will happen? So put the B is equal to infinity in above expression. Above expression was like 4 pi epsilon upon 1 upon A minus 1 upon B. So B को infinity रखा तो ये term 0 हो गया, ये A ऊपर चला गया. So capacitance will be 4 pi epsilon A. That's it. Simple. Case 1 for the mathematical purpose, nothing different. Okay. Let us go for case 2. Now this case 2 is very interesting. Consider that on the inner surface some coating of dielectric material having permittivity epsilon 2 is applied from A to R1 and radius of outer sphere is infinity. क्या कहा? A है. Then we will put some sort of dielectric material coating on this sphere, and this coating will have a radius R1. Okay, and we will have our outer plate B at infinity. ये उनका कहना है. यहाँ पे रखा है epsilon 2 permittivity of the material. Okay. This structure acts as two capacitors, one having permittivity epsilon 2 from A to R1 and second having permittivity इप्सिलॉन 0, ये जो नेक्स्ट पार्ट है यहाँ का परमिटिविटी इप्सिलॉन 0 फ्रॉम R1 टू इंफिनिटी. सो टू कैपेसिटर्स आ गए. So V is equal to minus integral initial to final E bar dot dl bar. We've seen this expression previously. So V is equal to minus R1 to A E bar dot dl bar minus integration infinity to R1 E2 bar dl bar. Okay. So do note towards the integral limit. अगर integral limit wrong हो जाते हैं तो you will end up into some kind of different observation. So do you remember that integral limit कहाँ से है? बाहर से अंदर की तरफ है. Okay, integral limits बाहर से अंदर की तरफ है. So first capacitor, what we have R1 to A integral limits. Second capacitor we will have infinity to R1. Okay, तो उतना ध्यान में रखना है so that your derivation will be kind of easy. So first capacitor with relative permittivity epsilon 2 has integral limits from R1 to A. And for second capacitor with permittivity epsilon 0 has integral limits infinity to R1. Okay, तो ये ध्यान रखना है. Now we will have E1, E2 and DL bar and we will put those values into V, expression of V. Okay, this is what we discussed about. So electric field 1 is equal to Q upon 4 pi epsilon 2. Okay, थोड़ा सा ध्यान रखिएगा कि भाई कैपेसिटर 1 है, capacitor 1 will produce electric field intensity 1 E1 has relative permittivity epsilon 2. Capacitor 2 will produce E2 bar. It has dielectric permittivity as epsilon 0. Okay. We are referring to AR cap because everything will be radially outward direction. Spheres. Okay. Sphere cylinder. We usually have AR cap, radial directions. Okay. And E2 has Q upon 4 pi epsilon 0 R square dot AR cap. Fine. So put the values into the expression. In both cases, our DL bar will be dr AR cap. So we have wrote these dr dot dr AR cap. Okay. So do the mathematics and take out few constants from the integral. So we will have some kind of expression over here. Okay. So in the first integral, we do have this term as a constant. In the second integral, we do have this term as a constant. Negative sign stays as it is. Okay, and this integral dr upon r square and dr upon r square has a value minus 1 upon r. Okay, क्यों आया भाई 1 upon r square dr. So this is nothing but r raised to minus 2 dr. इंटीग्रल सॉल्व करते वक्त क्या होगा, इसमें प्लस आ जाता है, एक ऐड करते हैं ना, इसमें +1 करते हैं जब इंटीग्रेशन सॉल्व करते हैं. सो वी विल हैव ये जो रिजल्टेंट है दैट विल बी -1. ओके, अपॉन -2 + 1 will be r raised to -1. So 1 upon r. Okay, this is the integral and you will have the values of the lower limit and upper limit. So we do have -1 upon r, r1 to a, and -1 upon r infinity to r1. So put the values we will have. Okay, from this we will have क्या कहते हैं उसको q upon 4 pi as a common. In the first term we have 1 upon epsilon 2. Put the limits 1 upon a. ये जो निगेटिव था ना, ये निगेटिव निगेटिव यहाँ पे मर्ज कर दिया, ये निगेटिव निगेटिव यहाँ पे मर्ज कर दिया. ओके, so 1 upon a minus 1 upon r and 1 upon r1, because we know that 1 upon infinity is going to be 0. Okay, so doing this mathematics, so put the value of v in the expression of capacitance, that is c is equal to q upon v. So we will have a whole equation like this. Okay, where q upon 4 pi epsilon got vanished. तो यहाँ पे q upon 4 pi epsilon था, sorry 4 pi था और यहाँ पे q था, तो q get cancelled out and 4 pi went to the numerator. So we do have kind of expression 4 pi upon 1 upon epsilon 2 and the equation. Okay, so this is an equation which talk about the capacitance. Okay, so total capacitance for this structure can be written as in a different way as in general 1 upon C is equal to 1 upon C1 plus C2. ये कहाँ से आया? We know that if two capacitors are connected in series, तो उनका equivalent capacitance ऐसे लिखते हैं. So if you look at our geometry, we do have a kind of geometry like this, epsilon to epsilon 0. So we do have one capacitor over here and we do have another capacitor over here. So C1 and C2, and both these capacitances are in series, so equivalent capacitance can be written as this. Okay, 1 upon C is equal to 1 upon C1 plus C2. So we can write down, okay, we had an equivalent capacitance C expressed in this way. Also, we know that this one. So taking reciprocal of this equation. तो 4 पाई नीचे चला गया, न्यूमरेटर नीचे गया, डिनोमिनेटर ऊपर आया. सो वी विल हैव 1 upon 4 pi epsilon to 1 upon a. एक पहली टर्म आ गई प्लस ये दूसरी टर्म आ गई. ओके, so I can say that okay, 1 upon c is equal to something plus something, and this something is nothing but 1 upon c and 1 upon c2. Okay, so we can write down, okay, 1 upon c1 is equal to something and 1 upon c2 is equal to something. So once again taking the reciprocal, so we will end up into the value of capacitances c1 and c2 of individual capacitors. The whole analysis was targeted to find कि भाई ये जो रीजन है ये कितना कैपेसिटेंस प्रोवाइड करेगा और ये वाला रीजन कितना कैपेसिटेंस प्रोवाइड करेगा. ओके, सो वी डू हैव दिस कंप्लीट डेरिवेशन और इसके ऊपर न्यूमेरिकल आते हैं वेयर वी नीड टू अंडरस्टैंड understand and apply these formulae C1 and C2. Probably you will not be asked to solve the derivation in the online examination, but yes, you will have the numerical based on C1 and C2. Okay, moving on to next part, coaxial cable. यहाँ पे interesting things once again happens because we do have a kind of spherical geometry, but really not spherical. We do have cylindrical geometry, but a cross section area. The cross section of the cylinder looks like the cross section of a sphere. Once again, same kind of assumptions are there. Internal sphere, internal cylinder. Oh, sorry, here we are considering the cylinder. Internal cylinder do have a radius A. Outer cylinder has a radius B. And in between somewhere we consider imaginary surface. It is having a radius R. Okay. Whenever we say that imaginary surface, it is called as a Gaussian surface, and it is only for the sake of mathematics. Okay, so let us go through the assumption. It consists of two cylindrical conductors of radius A and B respectively. If gap is filled with some dielectric medium, the structure acts as a capacitor. Let plus rho L is a line charge distribution present on the inner cylinder. Then according to Gauss law, we can say that minus rho L, negative line charge density, will be developed on the outer cylinder. Okay. Now we know that V is expressed as वेट भाई एनिमेशन तो बहुत है. हाँ, ओके. V is expressed as minus integration b to a e bar dot dl bar. ये क्या है? आउटर रेडियस है. आउटर रेडियस. ये क्या है? इनर रेडियस. ओके, so we will have outer radius to inner radius e bar dot dl bar. So we will have minus integration b to a rho l upon 2 by epsilon r ar cap dot dr ar cap. This is the electric field intensity due to an line charge. Okay, so ar cap dot ar cap will be 1 and we will be left with the integral sign. Okay, and we have minus rho l upon 2 pi epsilon 0 dr upon r integration b to a. So we will end up into ये जो है इंटीग्रेशन 1 अपॉन आर डी आर इज नथिंग बट ln ऑफ आर. अगर इंटीग्रल लिमिट्स b टू a है तो b टू a है. ओके, सो व्हाट वी विल राइट डाउन ln ऑफ a माइनस ln ऑफ b. ओके, वी आर अकोमोडेटिंग दिस नेगेटिव साइन. अगर मैं ये नेगेटिव साइन यूज करना चाहता हूँ, यहाँ पे ब्रैकेट के बाहर नेगेटिव साइन है, सो वी कैन राइट डाउन, ओके, let us use the negative sign that will represent our expression as ln of b, ln of b minus ln of a. So whenever we do have this kind of term, we can say that okay, this is nothing but ln of b upon a. Logarithm है भैया everything. So we end up into a kind of formula where rho L is line charge density, B is radius of outer cylinder, A is radius of inner cylinder, R is an imaginary surface in between these two, sandwich in between two, बाहर नहीं जा रहा है, उसी के अंदर है. Okay. So we know that C is equal to Q upon V. So Q is nothing but rho L up into L. Q है क्योंकि we know that line charge density is equal to total charge upon total length. So total charge है Q, total length let us assume L. So we can say that Q is equal to rho L into L. और V का एक्सप्रेशन तो अभी है अपने पास, तो पुट अप करो. Rho L will get cancel out. ये 2 pi epsilon R will go to the numerator and we will have the value of capacitance as 2 pi epsilon L upon ln of B upon M. Do you remember that ln is nothing but your logarithm to the base E. आपको कैलकुलेटर पे ln का बटन दिया हुआ है. Whenever you are going to do the calculations, use that button. Don't use log button because that log button represents to the base 10. Okay, ln का बटन आपको कैलकुलेशन करते समय यूज करना है. Okay, so what we will require to find the capacitance of a coaxial cable, we will require its length. भाई केबल कितना लंबा है, we will require its permittivity and what are its another dimensions. Radiuses रेडाई कितने हैं. Okay, रेडाई कितने हैं. So ये अगर quantity मिल जाती है आपको तो you can solve the numerical based on the coaxial cable capacitor. Straightforward. Only put the values and get the answer. That's it. We are going to discuss about the Laplace and Paulson equation in unit number 3. Okay. Or shall I discuss this one because it is nothing to do with magnetostatics. Let us discuss this one. Okay. According to point form of Gauss law, that is your del dot d bar is equal to rho v. Okay. Something happened. Oh, I got some color combinations over there. Pardon me for a moment, please. I gave them color coding. We are going to look at the Laplace and Paulson equation, the two mathematicians. Okay. And they do have a very deep contribution to the magnetostatics and electrostatics. Okay. And these equation actually, what equation we are going to see, those equation do represent your behavior of the electric field um, and your electric potential. Okay. One moment, please. Some little problem with the slide. One moment. Okay, and now I do have a little bit correction over there. Got it. Let us go back. So according to Gauss law, we have del dot d bar is equal to rho v, equation number 1. Since d bar is equal to epsilon e bar, so we can write down, okay, put the value of d bar into the above expression. तो यहाँ पे d bar रख दीजिए. So del dot epsilon e bar is equal to rho v and therefore we can write down, okay, epsilon तो वैसे भी constant है. Okay, तो उसके ऊपर partial differentiation का कुछ impact नहीं होगा. So we can write down del dot e bar is equal to rho v upon epsilon. Okay, according to equation of gradient. Okay, gradient का equation क्या है? E bar is equal to minus del v. potential, negative gradient of the potential. Therefore, we can put this value. We can put value over here. So we do have minus del dot del V is equal to rho V upon epsilon. So therefore, we can say that, okay, fine, del dot. So V is equal to negative लेके गए minus rho V upon epsilon. We are looking at the mathematical explanation, and this mathematical explanation has been observed, has been developed on the period of 100 years. So don't worry if you do not digest it, but yes, this is obvious कि भाई एक टर्म है उसके अंदर दूसरे टर्म का सब्स्टिट्यूट कर लिया. So whenever we say that, okay, del square V is equal to minus rho V upon epsilon. It is called as a Paul's equation. It says that the potential distribution depends on the local charge distribution. मतलब क्या? जितना rho v बड़ा होगा उतना ही आपका potential बड़ा होगा. Definitely. Okay, fine. The more the volume charge of volume charge density, potential will be different. So potential will be bigger. What negative sign indicates? Negative sign indicates your uh, potential difference is going to reduce. Okay, your potential difference, the V, is going to reduce as you move, you move away from the volume charge. Okay. यहाँ पे कुछ potential रहेगा, यहाँ पे कुछ potential रहेगा, and this potential is going to reduce as you move from away from the volume charge. Another very interesting thing, if की बात है, if rho v is equal to 0, then अगर volume charge density 0 है, then del square v is equal to 0, and this is called as your Laplace equation. Okay, यहाँ पे आपको ज्यादा डीप में जाने की जरूरत नहीं है, क्योंकि इफ रो वी इज इक्वल टू 0, भाई कोई भी बता देगा, 10th स्टैंडर्ड का भी बता देगा, अगर चार्ज नहीं है तो पोटेंशियल कहाँ से आएगा. ओके, बट in the mathematical way, so we started with d bar, del dot d bar is equal to rho v. Here we put the equation of E bar. Okay, so we end up into some sort of expression over here. Then बाद में यहाँ पे E में क्या रखा, minus gradient of V. Okay, so d bar में e bar में potential, and we end up into first equation Paul's equation and second equation as a Laplace equation, and that says few things. In practical cases, neither the charge distribution nor the potential distribution is specifying, and the electrostatic conditions charge and at some boundaries. ये जो है ना चार्ज डिस्ट्रीब्यूशन, रो वी, रो एल, रो एस, ये न्यूमेरिकल करने के लिए बढ़िया है, बट एट एक्चुअल अपने को पता नहीं होता है. एट एक्चुअल व्हाट वी नो, कितना वोल्टेज है, कितना इलेक्ट्रिक फील्ड है, वो चीजें वी कैन मेजर. Okay, so these types of problems are known as electrostatic boundary value problems. For these types of problem, the electric field intensity and the potential V are determined using Paul's equation and Laplace equation. Okay, तो यहाँ से सारी चीजें निकलती है in a practical cases. ये कहाँ पे यूज होगा ये दोनों इक्वेशंस? ये आपके यूज होते हैं सिमुलेटर्स में. जो भी आप एकदम हाई एंड सॉफ्टवेयर देखते हो ना, उनके बैकएंड में ना ये इक्वेशन रन करते हैं. ओके, सिमुलेशन करते समय डू द कैलकुलेशन, जैसे आपने मल्टी सिम यूज किया होगा, या फिर ये कटिया प्रो, ये जो बड़े बड़े सॉफ्टवेयर है, मैटलैब है, एट द बैक एंड यू विल हैव ओनली दिस कैरेक्टर प्लेइंग रोल. कभी डॉट के साथ डाइवर्जन, कभी क्रॉस के साथ कर्ल, एंड कभी कभी स्केलर के साथ वी ग्रेडियंट. ओके, सो दिस पैरामीटर टॉक्स अ लॉट अबाउट मैथमेटिक्स, एंड एज अगर आप कभी सॉफ्टवेयर डेवलपमेंट में या मेंटेनेंस में गए एज अ करियर, सो यू विल फाइंड कि भाई अच्छा होता था अगर मैथमेटिक्स पहले ही सीख लेते थे, अगर हमने मैथमेटिक्स में पहले ही इंटरेस्ट दिखाया होता. ओके, विद दिस से वी आर एंडिंग आवर सेशन. डू यू हैव एनी डाउट regarding probably understanding or something different? Okay, probably not. Fine. Hey Ram, okay, चलो ठीक है फिर. I will stop the recording now.